Optimization as a subject is very close to my heart. Optimization is a generic name given to the process of maximization and minimization. Long back, more than 24 years ago, no, not more than 23 years ago, I landed up in the Indian Institute of Technology, Kharagpur, not knowing what to do as a PhD student of mathematics. Well, I remember my teacher taking me down to my doctoral supervisor, taking me down and handing over a paper which actually changed my life, and I had no idea about the subject of optimization. What does it mean and what does it do and why it is important as a. So, optimization is not just an application of calculus, it is also a subject by itself. Today, through this dialogue that I am going to have with you, I am going to bring about the nature of optimization problems and how we deal with them. There are very, very subtle things that we need to know about optimization problems, and that is exactly what I am going to talk about. So, what we have been discussing till now while finding a maxima and minima is the following. That I want to find, I have a function from R to R and f is differentiable, and if f is differentiable, now trying to find its maxima and minima. We have already written down, if we just recall, that our first step is to find a point x dash such that f dash of x is equal to 0, and the second point is to make a check f dash of f double dash, if double dash exists at x star, either it can be this or if it is this, then this gives you a strict local mean and this gives you a strict local max. It tells you that x star is strict local mean and x star is strict local maximum. But what about this situation? When having second order derivative may not always be of help. You might say, oh, this is the situation where x star is possibly not a maximum minimum, because most of the cases in such situations in your mind you will keep the function fx is equal to x cube. So, at fx equal to x cube, this point x star equal to 0 is obviously neither a maximum or minimum. If the function decreases, it becomes negative after 0 and becomes positive on the right hand side of 0. So, and you know in this particular case f double dash x is equal to 0, because f dash x is 3x square and f 6x is f double dash x, so at 0 it is 0. But that is really not the issue. I will give you an example of a function where the first derivative is 0 at a point at 0, in fact the second derivative is 0, but 0 is the minimizer. This function is slightly steeper than y equal to x square, and this function is, this is the graph of the function y equal to x to the power 4 or fx equal to x to the power 4. So, what is, so if fx is equal to x to the power 4, my f double dash x, sorry, f dash x is 4x cube and f double dash x is 12x square. So, f dash 0 is 0, f double dash 0 is 0. But you know that x4, fx is x4, so it is always greater than equal to 0. So, fx and f0 is 0, so fx is greater than equal to f0, so 0 is the minimizing point. So, x star equal to 0 is the minimizing point, but f double dash x is equal to 0. it does not give me any information. So, what are you going to do? Try with third derivative, fourth derivative, what? Here once the second derivative also fails to give me some information, we should look, rather try to draw the graph by current softwares, or we should rather try to look into some more other properties of the function which might just tell us that okay, if f dash x star equal to 0, if the function has this additional property, then you get your minimizer. And what is that property? What is that property that will tell me that thing, that okay, your second order information has failed, but maybe there is some additional property which I can attach with f dash x star equal to 0, which will tell me immediately that x star is the solution. Such property of a function is called convexity. So, by discussing about optimization, I bring you to one of the most important aspects of optimization, that is studying of the optimization of convex functions. So, what is a convex function? A function f, say from R to R, or if you want a function f from AB to R, is convex if for all xy element of R or AB, does not matter what you want, and any lambda given in 0 1, f of lambda y plus 1 minus lambda x is less than equal to lambda fy plus 1 minus lambda f of x. This is true for any lambda between not 0 and 1. So, if you take two real numbers, you must have studied it in coordinate geometry. If I take two real numbers x and y, and if I make this combination z equal to lambda x plus 1 minus lambda y, where lambda is some number between 0 and 1, maybe I should call it z lambda, then what sort of points z lambda satisfies? Where does z lambda lie? Is z lambda less than x? Here suppose I know that x is bigger than, x is lesser than y, suppose I know this. Then is z lambda less than x, or z lambda in between these two, or z lambda is outside? This is something let us figure out. So, what happens? So, suppose I choose lambda equal to half, then what is happening? It tells me it is nothing but half of x plus half of y, which is x plus y by 2, which simply means is the midpoint. Okay, this is the midpoint. So, which means now if I put lambda equal to 0, I get y, sorry, or maybe I should write it like this, lambda y plus 1 minus lambda x, that is what I have put there. Sorry, I just make this change. So, if I put lambda equal to 0, z lambda is equal to x, and if I put lambda equal to 1, this lambda equal to 0. So, if lambda is equal to 1, then z lambda equal to y. and between 0 and 1 half lies. So, you can immediately see from an intuition that if I move, so this x actually corresponds to the point lambda equal to 0 and this corresponds to the point lambda equal to 1. So, if I have move z from 0 to 1, lambda from 0 to 1, the z lambda points are all the points which are lying between x and y. So, basically then z lambda, each z lambda belongs to this, or rather the collection of z lambda where lambda belongs to 0 1, this set is nothing but the interval, closed interval xy. So, what does this definition signifies? It tells you, I want you to figure it out yourself, that if you take 2 points on the graph of the function and join them by a chord, okay. So, this is my x and this is my, or this is my y and this is my x. So, this is my x fx and this is my y fy. So, let me take some z lambda. So, this is z lambda. So, that is lambda x plus 1 minus lambda. So, what is the value of f of z lambda? This is the value of f of z lambda. And what is lambda fx and lambda fy? So, this is my fy value, this is my fy and this is my fx. So, lambda fy plus 1 minus lambda fx is some point here, and if I draw a line parallel through it to the x axis, it will cut it here. So, the functional value of this 2 is here, is bigger than this. That is exactly the meaning. And you see what it says, it essentially says that this is only possible, this fact is only possible if, if I draw the graph, if I draw this chord, this chord always lies above the graph of the function. In the sense, not above the graph, a part of the graph of the function is always below the chord. That is the point z lambda, where you have the z lambda, that would always lie below, that part of the graph would always lie below this straight line. A more beautiful and simple explanation comes if we just go slightly into higher dimension for a while. So, we have been in R, but you are already conversant with the xy plane. So, let me go into a higher dimension and define, for example, what is called a convex set. So, let me go in 2 dimensions, right. So, let me go in xy plane. Let me look at a set like this. So, now this is a point and this is a point, and this point could be x, so this is my set C which has all these points inside, and I take any 2 points and join them by a straight line. So, this is the line segment joining the 2 points. Maybe my drawing is so bad. Okay, this is the line segment joining this 2 point. How do I express this point? And you know this very well, you know this very well from your coordinate geometry, that if so if I want to take any point here, so how do I describe it? So, suppose this point is given by x1 y1 and this point is given by x2 y2. So, this is my x2, this is my x1, this is my y1, this is my y2. You know that suppose this is my some point z lambda, right? Z lambda, what is a two-dimensional point with z lambda 1 and z lambda 2 as the two coordinates. Now what is happening? You just drop a perpendicular here. Now this divides the line into two ratios, m by n, and then you know how to find the coordinate of this point. It is m of x1 plus n of x2. So if you have 2 points x1 y1 and x2 y2, then any point z lambda, this point is whose the coordinates would be of this form, lambda x2 y2 plus 1 minus lambda x1 y1, which is same as where lambda is obviously between 0 and 1. So I am joining the line segments, right? And here if I do some additions the way vectors are added. So if you have x1 y1 and x2 y2, they represent the two vectors, then the new vector, when you add the vectors in the standard way of adding to geometrical vectors, then the new vector, the tip of the new vector has the coordinate x1 plus x2 and y1 plus y2. So I can anyway multiply this lambda inside, basically you are increasing the length of the vector. So it will become lambda x2 plus 1 minus lambda x1 would be the new coordinate of the vector. This is nothing but scalar multiplication of the vector, and lambda y2 plus 1 minus lambda y1. So this is the coordinates of the point z lambda, where lambda is between 0 and 1. So a convex set is a set, where if you take any 2 points and join them by a line segment, then the whole line segment lies in this set. The human body is not a convex set, because if I take a point here on my head and a point in my shoulder, I join them, then you see the whole line segment except these 2 points are outside my body. So body is not a non-convex thing, but convex sets are very common in mathematics. So a set is convex if I take any 2 points inside it. A set in R2 is called convex if I take any 2 points inside it, and then these points must also be inside the set C for any lambda between 0 and 1, and where x1 y1 and x2 y2 are 2 arbitrary points. Now what is so important about getting to this definition? See, another way of recognizing a convex function is this. You take a function like this and you shade the part above the graph of the function. So now once you shade the graph of a function, if you take a function from R to R, then what is the graph of a function? So the graph of a function f, it is the set of all coordinates x, y, such that y is f of x. And so this is now in 2 dimensions, it is in R cross R, it is in the Cartesian plane. So if you shade this part and just check whether this is a convex set, then you can immediately guarantee that the function is convex function, and this definition exactly tells you this. And this, anything which is above the graph is called the epigraph. So function is convex if and only if its epigraph is convex. So this is a very, very important statement which I want to write it down here. So what is my epigraph? Epigraph of this function f is a set of points x, y in R2 such that f of x is less than equal to y, and f is convex if I am just considering functions from R to R. So we can later on do it for AB to R. You can do those extra technicalities. If only if x is, if and only if APF is a convex set in R2. So, this is a very important learning, and I will tell you why we are so much bothered about convex functions. Convex functions brings us into a world where there is no local minimizer, whereas there does not exist any local minimizer. That is, if you want to minimize a convex function over a convex set, for example, an interval is a convex set. So, in real line, a convex set is either the empty set, by convention a single point, or a closed interval. So, if you want to minimize a convex function over an interval a b, then there is no local minimizer. Every local minimizer is global. So, if f from R to R is convex, then so it does not matter. So, even if I do not take this AB, forget this AB, forget this interval, then every local minimum is global. This is a very important point. So, A is a global minimum point. So, how do we really prove this fact when you consider convex functions which are differentiable? Of course, there are convex functions which are not differentiable. I will simply give you the most standard example. If x is equal to mod x at x star equal to 0, the absolute value of x, if x is absolute value of x and you have x star equal to 0 at its minimum, but you know at x star equal to 0 there is no derivative, but if you look at the epigraph, you immediately know that the epigraph is convex and this the function is a convex set. So, convexity also takes us into a different realm, completely a new realm in optimization and mathematics. It takes us into the realm of non-differentiable optimization, that we have to face the hard reality that there could be non-differentiable problems which might have an optimum point or minimum point, and they may just occur at the point where the function is not differentiable, and this happens pretty often with convex functions, but we are not going to get into such details. So, now how do I prove this fact? So, my function is differentiable and convex is okay. If you want to say is differentiable and convex, then every local minimum is global. So, how do I prove? On what basis I am making such a statement? This is a very, very amazing statement. So, if your second derivative fails, for example, if you look at x4, so look at the epigraph. The epigraph is a convex set. So, immediately you know if it's a convex function, if the derivative, second derivative has failed, and if the convexity check comes through, then I am done. But how do you check the function is convex? Of course, you can draw the graph and try to do this, what I just told you. If I have a twice differentiable function, if f is twice continuously differentiable, then f is convex if and only if f double star x is greater than equal to 0 for all x in R. So, this is a very, very important concept. This is one of the important application of Taylor's theorem, which we will show you when we will discuss Taylor's theorem. This is a very important application of Taylor's theorem. So, I am just building up the subject. You see that the certain things which will come later, and we will show that these results are actually applications of a lot of mathematics, a lot of analysis, a lot of optimization, essentially bears itself on something called Taylor's expansion, which will come towards the end of the course. And so, okay, so that is one way. For example, if I take x4, what is x, f double dash x, it is 12 x square. So, no matter what is your x, you are always getting a non-negative. This is always greater than equal to 0. So, immediately you know it is convex. So, once it is known to be a convex, then any point which satisfies f dash x equal to 0, if there is a local minimum, it will satisfy this, and that immediately will give us a global minimum. Why? I will tell you the reason. Here again we will use our geometrical idea. Now suppose I take a convex function, and now let me take a point x f x. This is x and this is a point x f x. Let me draw a tangent through x f x. Once I have drawn a tangent through x f x, observe what is this. Oh, observe this. Observe what is happening. The tangent line is lying below the graph of the function, or lying below the epigraph if you want to say like that, lying below the graph of the function. So how do you express this fact? Take any other point y, and this is the y value on the tangent, and this is the y value of the function. Say let me call this y hat, and this distance is fy. So what is there? Fy is greater than or equal to y hat. Or what is y hat? You know that y hat, we have already found out the equation of the tangent line in the previous lecture also, is nothing but f of x plus f dash x, which is the slope of this tangent line, into x minus, into y minus x. This is exactly y hat, right, at the point y. At this point y, this is the value of the, so corresponding to this y, you draw a perpendicular line, it cuts the tangent at the point y hat. So this is the point which is y hat, and this is the point which is y fy. So what does it say? That fy is bigger than this y hat. So what does it say? It says that f of y is bigger than equal to f of x plus f dash x into y minus x. But this relation, so f is convex, this is true. If it is a convex and differential function, this is true, and this happens for any yx, because we have just chosen two arbitrary points. This is a geometrical proof, this is not a rigorous proof. We will give you later on such rigorous proofs once we talk about Taylor's theorem. But what I want to tell you is this very fact is that you see that once I have done this, this is true for all x y in R. It is not some for particular x y, because I have just chosen arbitrary x y. You can take x here or y here or y here, x here, you do the same thing. You do the same thing, you get the same answer. Now suppose there is a local minimizer, okay. X star is a local minimizer of a differentiable convex function, So then how do I say that it is a global minimizer? You see, I will simply say, okay, let me take any point y in R, then if I take the if I take the pair y and x star, so for that particular pair this relation will hold true, because f is convex and differentiable. So f dash of x star into y minus x star. But now since it is already a local minimizer, we know that since f is a local minimizer, we already know that f dash of x star is 0. Since f is a local minimizer, since x star is a local minimizer, we know that f dash of x star is equal to 0, and let us plug that 0 in here. So it will implicate fy is bigger than equal to fx, f of x star. So this does not matter, whatever, I have chosen some arbitrary y in R. So this is essentially true. not essentially true, this is just a language the way I speak. This is true for every y in R, because your y was chosen arbitrarily, it does not matter, whatever y you choose, you make the pair y x star, on it you apply this fact and put f dash x star equal to 0 because it is local minimizer, this will always happen, and hence you will immediately get the fact that x star is a global minimizer. So what does it say? It not only proves that a local minimizer is global, it says that whenever you get for a convex function a point f dash x star equal to 0, that point is also a global minimizer. So here you have two learnings, that there is no local minimizer for a convex function, everything is a global minimizer, and whenever f dash x star is equal to 0, that point is a global minimizer. For example, if you take x a cube, the point 0 is nothing, it is not a global or local minimizer, it is called a point of inflection where the curve changes shape. We need not bother that amount with such things, but this is very important. Two learnings, that any point f dash x star of a convex function, if it is 0, then x star is a global minimizer, and hence every local minimizer is global. Thank you, and hope that you enjoyed this new thing usually not told with such detail in calculus courses. Thank you very much.